Hey everybody, welcome to the shop. I'm Jarrell at Jarrell Education, and today we're going to be going over a classic physics problem called the Atwood Machine problem. Now, if my videos help and you like the content, please like and subscribe. It helps me know that I'm doing the right thing, and if there's anything that you'd like to see clarified, please leave a comment, okay? Because I always read all the comments. All right, let's get into it. All right, today we're going over a classic problem in a first-year physics class. It's called the Atwood Machine problem. All right, let's read the statement. Assuming that the pulley's mass is negligible, in the figure below, find the acceleration. We want the acceleration, and we also want the tension in the string. Okay, now the first thing I got to point out when we're doing this is that it's said in the statement of the problem that the pulley, the mass is negligible. And, you know, when you first start out, that's what you kind of need to do to get used to doing the problems. Now, later on, that's not going to be the case when we start talking about rotational inertia and all those kinds of things. So right now, we're just sort of leaving that out. So if that's what you're looking for, you're just going to have to wait for a later video on that one. So right now, this is just an Atwood problem where the pulley is not contributing or taking anything away from the system. Okay? Now, it should be clear that the one is 9 kilograms and the one is 6 kilograms. The 6 kilogram is going to get accelerated up, and the 9 kilogram is going to get accelerated down. And since they're attached to a string where there's no looseness in the string is taut, the acceleration they're going to have, the numerical value of it's going to be the same. So here's how I'm going to show you two different ways to look at this. All right, here's the first one. Now, the first question I want to talk about, though, before I even get into that, is I want you to ask yourself, do you know why on a number line we sort of made numbers to the right positive and numbers to the left of 0, we made those negative? All right, so just pause the video and see if you can answer that. Now, as far as I know, I mean, I could be wrong, but as far as I know, I think the reason that they chose that, it was arbitrary. I think there was more right-handed people, and so that's what they picked to be positive. But they didn't have to choose it that way, okay? They could have picked left to be positive and right to be negative. And sometimes that's going to be a more convenient thing to do, as you're going to see here. So watch, here we go. Now, if I take the 6 kilogram mass and I draw a free body diagram, so there's 6 kilograms, I know that I have mg down. Now I'm going to let g be equal to 10 meters per second squared instead of the normal 9.8. Now on the AP Physics 1 exam, if that's what you're taking, they usually use G equals 10. So that's what I'm going to do too. It makes it easier to talk about with the numbers. You know, you don't have to grab a calculator all the time as often. But you know, if you're going to use 9.8, that's fine. All the same principles still apply. Now then I have an upward force on the 6 kilogram mass, which I'm going to call tension. And I want to point out tension, I'm drawing it larger than mg. It's longer because the 6 is going to accelerate up. And then I'm going to apply Newton's law. So the summation of all the forces is equal to ma. And I would have this, T minus, now remember, mg in this case is actually going to be 60 because the mass is 6 and g is 10. So that's going to be 60 newtons. So it's going to be T minus 60 is equal to 6a. Now this is great. The problem is I have one equation and I have two things I don't know. So that means I need another equation. Now where am I going to get that from? I'm going to get that from the 9 kilogram mass. So let's draw that. So I've got the 9 kilogram mass. Okay. Now it's going to have a downward force also of mg, but in this case mg is going to be equal to 90 newtons because the mass is now 9. And the tension, now this is what I want to talk about. The tension going up is still going to be tension. It is the same rope, so it's going to have the same tension going through it. Now, please, I want to point out at this juncture, right, that's not going to always be true. The tension's not going to be the same throughout. The only reason that's true now is because the mass of the pulley doesn't count. All right. Later on, the problems are going to get more complicated, and it will. But for now, they both have, you know, the 6 is being pulled up and it's accelerating up. The 9 is also being pulled in the upward direction, right? They both have a tension in them, but the 9 happens to be accelerating down, which brings me to my next point. In this case, all right, the force that's winning out is the 90 newtons, whereas in this case, the force that was winning out was the tension because it was being pulled up, and that's the way it was accelerating. So what we're going to do is we're going to define positive to be the direction that the mass is accelerating in. And in this case, for the 9 kilogram, that would be down. So when I write Newton's law, I'm going to write the summation of all the forces is equal to ma. But now I'm going to say this. I'm going to say 90 minus tension. Even though tension's up, I'm making it negative because it's not accelerating that way. It's accelerating downward. And that's going to be equal to 9a. And notice that one has 2 unknowns in there as well. But now I've got 2 equations. So let me rewrite them over here. The first one, this one, is t minus 60 is equal to 6a. The second equation, that's this one, I'm going to write it the same equation. I'm just going to switch the terms. Negative t plus 90 is equal to 9a. I didn't change anything. I just wrote the tension term first. Now, when I combine, so what I'm going to do is I'm going to solve these 2 equations simultaneously, right? And I'm just going to add them together because it's nice. The t's already cancel out. So when I add these 2 equations up on the left, the t's cancel out, and I end up getting 30 is equal to 15a, which means the acceleration, when I divide both sides by 15, is going to turn out to be 2. And the unit on that would be meters per second squared. So there's the acceleration. Now, if I want to find the tension, all I have to do is take A, which I just found, and plug it back into either one of these 2 equations. So I'm going to use the first one. So t minus 60 is equal to 6 times 2. So I get t minus 60 is equal to 12, which means t, I'm going to add 60 to both sides, would be equal to 72. And that would be in newtons. Okay, now we're going to solve the same problem, but we're going to do it a slightly different way. All right, now here's the way I want you to think of it. You got the mass. I'm just going to redraw this because it's going to make it easier for me to explain what I'm trying to say. So here's the pulley, and here are your 2 masses hanging off, right? Okay, one of them is 6 and one of them is 9 kilograms. Okay, now gravity's pulling the 6 down that way and it's pulling the 9 down that way. But what I'm going to do, all right, is I'm going to sort of pretend, if you can follow along here, I'm going to keep the forces all the same way, but I'm going to pretend I'm going to swing the 9 up and I'm going to swing the 6 up, and I'm going to look at it this way. I've got a 6 kilogram mass here, right, connected to a string to a 9 kilogram mass there, and there's a force this way that's going to be mg for the 9, right? So remember, if you remember back in the last problem, you can stop and scroll back to that. That was 90 newtons because that was just equal to mg where I was looking at the 9. And then I'm going to have a force this way of 60 newtons because that's that mg. In other words, this is the 60 here, right, which is pulling down. This is the 90 here, but if you imagine, sort of like in time lapse, I took these masses and swung them up so they're like that, and I'm pretending gravity's pulling one that way and gravity's pulling the other one that way. That's what I just drew. And now if I sort of put a box around them, like that, and I just ignored the tension for the time being and pretend that they're one mass, I could say this: the summation of all the forces is equal to ma, right? Now what I've got is 90s to the right, so I'll make that positive, and 60s to the left, and I know it's going to accelerate to the right, so the right direction is positive, like I said before. So this would be 90 minus 60 is going to be equal to 15a, and I get 30 is equal to 15a, and the 15 is coming from me just adding the 9 and the 6. So I divide both sides by 15, and I get a is equal to 2 meters per second, just like I did before. Okay, so now I know those masses are accelerating, right? They're accelerating with an acceleration of 2. And now all I'm going to do is I'm going to look at the 6 kilogram mass, right? So let's take a look at that by itself, and let's draw the free body diagram. So I've got a tension force pulling it that way, and I've still got the 60 newtons pulling back. That's 6 kilograms. So in this case, apply Newton's law. Summation of all the forces is equal to ma. So t minus 60 is going to be equal to 6 times 2, and I get t minus 60 is equal to 12, which implies, when I add 60 to both sides, that t is equal to 72 newtons, just like it was before. Okay, so you can look at the problem either way. You can do it that way, or you can do it the first way. I mean, personally, I like doing it the first way. That's up to you. All right, done.